In the previous lecture, we went through a method for indexing the powder diffraction pattern of a cubic material. And as we saw, in a cubic material, one variable determines the positions of all of the diffraction peaks. Now, as the symmetry of the crystal decreases, then we have more degrees of freedom in the size and shape of our unit cell. Right? There are more variables involved in the indexing process. As a general rule, we're going to have to resort to computer programs for indexing most powder diffraction patterns. But if we don't decrease the symmetry too much, either to the tetragonal or hexagonal crystal systems, where there are two variables which define the size and shape of the unit cell, it is still sometimes possible to index these patterns manually. And we're going to go through a couple of examples in this lecture. All right, let's start with this powder pattern. We don't know what it is. However, there are not too many peaks in the pattern, so that suggests the symmetry might not be too low. If we were to look at the spacing of the peaks, it isn't that nice regular repeating pattern we saw in the last lecture for a cubic crystal. That's kind of hinting at the fact that we might be at a lower symmetry here. But let's go through the procedure and first try to index this as though it were a cubic crystal. So if you remember from last time, the next step is to convert these two theta values into d spacings. So we can use this form of Bragg's law to do that. And then we get this table of d spacings. The next thing we do is we're going to calculate 1 over d squared values. All right, so if I take each of these d spacings, invert it and square it, then I get this column of numbers. If we have a cubic crystal, we should have a common factor that when multiplied by an integer will give us all of these values. And the procedure we used last time to come up with that factor is to assume that the first peak is the 1, 0, 0 peak, in which case the d spacing of that peak becomes the unit cell parameter. So if we were to do that here and assume that the first peak is the 1, 0, 0 peak, and we look at our equation up here, which relates the d spacing in a cubic crystal to the values of hk and L and the lattice parameter, for the 1, 0, 0 peak, you can see this numerator becomes 1, and the dHKL is equal to A. Right, so we're saying that the A lattice parameter, the cubic unit cell constant, would be 4.69 angstroms. So when we do that, then we're going to divide all of these quantities by 0.045. Right? That would be the 1 over A squared value. That's our common factor. And if it is a cubic crystal, then these should all come up as integers. Now we saw last time that sometimes there might be some missing peaks, in which case the first peak might be not the 1, 0, 0, but the 1, 1, 0, or the 1, 1, 1, or the 2, 0, 0. And in that case, what we would see in these values is that although they might not all be integers, we should be able to multiply by a relatively small number and make them all integers. Well, that's not exactly true here. I mean, we do see some integers in there. We see a 1 and something close to 4 and maybe close to 3. 7, well, 7 isn't one we normally see, but here's a 9. But on the other hand, then we have some that are close to a half. Okay, we could fix those by multiplying by 2. But then what about, 7.61 or 6.09? What we're seeing here is there's no small integer that if we multiplied all these values by that integer would fix this problem. So it might not be a cubic crystal. Well, what if it were one of the lower symmetries? How would our analysis change? So these are the formulas that give us the d spacing in terms of the hk and L Miller indices and then the size and shape of our unit cell. You can see that for a tetragonal system we have 2 variables, A and C. For an orthorhombic, we have 3, A, B, and C. For the hexagonal, we're back to 2, A and C. And then in the monoclinic case, we have A, B, C, and beta. So there are 4 variables. Let's just focus on the ones which have two variables, the tetragonal and the hexagonal systems. So when we look at these formulas, we see that in each case there's two terms. There's this term, h squared plus k squared over a squared. Right? That's going to depend on the value of our a lattice parameter. And then we have another term, and that's going to depend on the value of our c lattice parameter. Okay, so that means we could divide those numbers by two different factors. The other thing to recognize is that now the integer values we expect to see are not going to be the same that we had with cubic. When we're taking two integers, squaring them and adding them together, we can get 1 if one of the integers was 1 and the other was 0. We could get 2 if both h and k were 1. We could get 4 if h was 2 and k was 0. 5, 8, 9, 10, and so on. Right? But we can't make 3 or 6 or 7 or, for that matter, 11. And then if we were to look at the second term, that one is pretty easy to see that we're only going to get integer multiples of the square of the integers. So 1, 4, 9, and 16. So that's the pattern we might see if we had a tetragonal crystal. For the hexagonal, it's a very similar sort of analysis, but the one difference is that this first term now is not the same as the tetragonal case. And so the integers that we're going to see for this first term are 1, 3, if both h and k are 1, 4, 7, 9, 12. So it's a different pattern of integers than we see in the tetragonal case. Here we can make 3 and 7, but we can't make 2. We can't make 10. And now let's go back to our table of d-spacings and see if we can make sense of it. Now, when we assumed that this first peak was the 1, 0, 0 or the 0, 1, 0, we do see some integers here. We see obviously 1. We're going to get that no matter what. Then we have, this one is pretty close to 4, although a little bit off. This one is pretty close to 9. So if the c lattice parameter were 4.69, we might expect to see only 1, 4, 9, 16, 25, and so on. Let's now assume, just as a guess really, that the second peak might be the 1, 0, 0. So if we do that, right, then we're going to divide all of these by 0.069. And here what we see is an encouraging pattern. Here's a 2, a 4, a 5. Right? That would be the pattern we would expect for a tetragonal crystal. Right? 1, 2, 4, 5. The next one would be 8, but we haven't measured out to high enough angles to see 8. All right, so that's encouraging. We also see maybe a couple of other things that should give us some heart. If we look at the 1 over d squared values of the first two peaks, 0.045 and 0.069, if we were to add these together, we would get the 1 over d squared value for the third peak. If we were to take 0.138 and add this 0.045 to it, we would get something pretty close to 0.184. Right? So another strategy that we're using when we're looking at these numbers is we're looking for common factors that separate two different peaks. So let's go forward with the assumption that the d-spacing of this first peak corresponds to the c-axis, and the d-spacing of the second peak corresponds to the a-axis. Now that we have these two values, we can calculate where all of the other peaks should be. I just kind of show that here for a handful of peaks. Right? I'm using this formula and these values for A and C, and then I'm using different values of HKL. These three peaks all have the same first factor, and then we're just adding differing values of this second factor, L squared over C squared. And you can see where the peaks would be located. Here I'm doing the same thing for the peaks where H and K are 1. And if we look at the 2 theta values of these peaks, we would see that all of them are in our powder diffraction pattern. And so if we go ahead and calculate where all of the peaks would be using this formula and these lattice parameters, then we can come up with an indexing for all of the peaks that we see in the powder diffraction pattern. So this is indeed a tetragonal cell. It's actually the powder pattern for lead vanadate. The space group is a tetragonal one, P4MM, and these are the lattice parameters of the crystal that was used to generate this powder pattern. The one thing I might note is if we look right here at about 38 degrees, there's actually two peaks, the 002 and the 111, which are almost but not exactly overlapping. You know, this can happen, and it also would point to the fact that the higher resolution that we have with our powder pattern, the better we might be able to see overlapping peaks, and resolving them would help us in the indexing process. Okay, let's see if you can index a pattern that's one of these higher symmetry space groups. Here's another X-ray powder diffraction pattern. If we look at it for a minute, we see there are not so many peaks there, and that does suggest a higher symmetry. But we also see that, you know, some of the peaks are closely spaced, and then in other places we have peaks that are relatively far apart. And that's telling us that it's probably not a cubic crystal. I want you to try to index this powder pattern. I'm going to help get you started and save you a bit of computations by giving you the values of the d spacing and then the 1 over d squared. So with these values and what we've talked about earlier in this lecture, let's see if you can index this powder pattern, and then if so, determine the value of the unit cell constants. One hint to keep in mind is that depending on the space group, we oftentimes might have some missing peaks. And in this case, there are some peaks that are missing, and the fact that peaks are missing does complicate the indexing process a little bit. Well, were you able to figure it out? Were you able to index it? Were you able to make any headway? It took me a little while to do this when I worked through it on my own, so don't feel bad if you weren't able to figure it out. But let's go through the approach to indexing this powder pattern. Okay, so the first thing we're going to do is let's assume that very first peak is a peak that has the lowest possible Miller indices. So if we were to assume that first peak is the 100 peak, we're going to divide all of the values in column 3 by 0.092. And when we do that, we would get this pattern. Okay, there are some integers that come out of this. A 1, a 3, a 4. That's kind of encouraging. Of course, there's a lot of peaks that are not explained. So maybe we should assume that, you know, the second peak is another low Miller index peak. Let's assume that the second peak might be the 001. So if we divide everything by 0.102, well, we get a couple more hits. So we've got maybe our foot in the door a little bit. I will say that the pattern of 1, 3, 4, that's what you would expect for a hexagonal crystal. So maybe this first peak could be the 100 peak of a hexagonal crystal. And we do see 1 and a 4 for the assumption that the second one is a 001. Well, if that were the c-axis of a hexagonal crystal, that's what you would expect to see 1, 4, 9. We don't go high enough in 2 theta to see the 003 peak if that assumption were correct. The other thing that's a little bit encouraging about these values we picked is if you take the first two peaks, 0.092, 0.102, you add these together, you get 0.194. So we have a common difference between 0.092 and 0.194 of 0.102. If we were to look at this 0.274 and we add 0.102 to that, we would get 0.376, and lo and behold, here's a peak pretty close to that. That's a good sign that we might be on the right track. Now, if our guess is correct, the next step would be to take our guess, determine the values of A and C, and then calculate where all of the peaks would be for those values of the lattice parameters. It's just a little bit more complicated for a hexagonal system than a tetragonal system, because in that first term, we have this 4/3 in there. So if we were to assume the first peak is the 1, 0, 0 reflection, and 1 over d squared is 0.092, then we plug in 1, 0, 0 for h, k, and l, and then we can solve for a. We would come up with the a lattice parameter is 3.81 angstroms. The c lattice parameter is more straightforward, right? We're assuming the second peak is the 0, 0, 1. Then this reduces to 1 over d squared equals 1 over c squared. And so the d-spacing of the second peak is the length of the c lattice parameter. So now we have a guess for the a and c values of our unit cell. Let's go back and calculate where all of the peak positions would be. You can do this manually. You could use a spreadsheet. That's what I did. You could use a crystal drawing program like Vesta or Crystal Maker. Any of those would work. When we do that, what we see is encouraging. We see that we can explain the positions of not only the peaks in red and blue, but we also can explain the positions of some other peaks. In total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks that are indexed with this assumption of a unit cell, and 3 that are not. Well, we might have an impurity. There could be a second phase in there that accounts for those other 3 peaks. Although here, I'm not giving you an example that has an impurity in it. On the other hand, the fact that we could index the positions of 9 peaks with just 2 variables suggests that we must be on the right track. And so what can we do to explain the positions of these other 3 peaks? Maybe we need to increase the value of one of our unit cell constants by an integer amount. So what I'm going to do is assume that maybe the c-axis should be not 3.13, but twice that value. Maybe for some reason, the 001 peak might be missing, and that second peak is actually the 002. That can happen if you have certain kinds of lattice centering, or screw axes, or glide planes. Well, if we were to double the length of the c-axis, what that would do to the indices is everywhere the c value now also doubles. Right? So if you can imagine a unit cell and you had the 0, 0, 1 planes, those lattice planes would be 3.13 angstroms apart. But now if we were to make our unit cell 6.26 angstroms in height, then the spacing of those planes still should be the same, but they're not the 001 planes anymore. They become the 002 planes. So if you were to compare these reflection indices to the indices given on the previous slide, you would see that everywhere the L parameter has doubled. Now, the other thing to note is in the indices that I've given here, all of the L values are even. What about now the L equal odd values that we could possibly see? Well, it turns out that we can now index these 3 peaks that we could not before, and all of them have an L value that's an odd number, 101, 103, 201. So now we've indexed all of the lines in our powder diffraction pattern. We have a unit cell that's still pretty small in volume and quite high symmetry. And so this is the solution. It turns out this powder pattern goes with zinc sulfide, which is a hexagonal crystal, and it has the dimensions very close to what we determined. The space group is P63MC. Now we will learn later on that when you have a 6/3 screw axis, the 00 L peaks where L is an odd number are all systematically missing. So that's why we don't see the 001 or the 003. And that's why this first 00 L peak is actually the 002. And here we see the 004. That kind of highlights one of the challenges we run into with indexing, that when we have peaks that are systematically absent in our diffraction pattern, it makes the guessing of what are the diffraction peaks a little harder. I should say in full disclosure that when I was preparing this lecture, I started with the structure of anatase. That's one of the forms of TiO2. It's a tetragonal crystal system. I thought that would be pretty straightforward, but it's a body-centered tetragonal crystal system. And because of the peaks that were missing, actually I could not index it, despite spending spinning a while trying to do it. We did have a couple of examples here where we were able to index tetragonal and hexagonal crystals by hand, but in general it's not that easy to do. So what we're going to do most of the time is rely on computer programs for indexing. That's a technique called auto-indexing, and in the next lecture we'll go over the considerations that we have to deal with when we do auto-indexing.